Type 2. This is the classic and most common way a massive star dies. A Type 2 supernova occurs when a star, more than about 8 times the mass of our Sun, runs out of fuel. Its iron core can no longer produce energy, so it collapses catastrophically under its own immense gravity. The core collapses into an ultra-dense object, launching a shock wave. In modern models, that shock initially stalls and is likely revived by neutrinos, turbulence, and hydrodynamic instabilities before the star's outer layers are expelled. The defining characteristic of a Type 2 supernova is the presence of hydrogen in its spectrum, because the star explodes before it has lost its outer hydrogen envelope. What's left behind is an ultra-dense remnant, either a neutron star or, if the original star was massive enough, a black hole. Type 1a. This type of supernova comes not from a single massive star, but from a tiny, dead one in a binary system. A Type 1a supernova is the thermonuclear explosion of a white dwarf, the compact remnant of a Sun-like star. If a white dwarf is in a binary system, it may gain material from a companion star or merge with another white dwarf, creating conditions for a thermonuclear runaway. In the classic model, the white dwarf approaches the Chandrasekhar limit, about 1.4 solar masses, and undergoes runaway thermonuclear fusion. However, some Type 1a explosions may occur below that mass through other binary-triggered mechanisms. Because many Type 1a supernovae have similar light curves and can be empirically standardized, they are useful distance indicators. This makes them powerful, standardizable candles, allowing astronomers to measure cosmic distances and the expansion history of the universe. Type 1b and Type 1c. These are the imposters of the supernova world. They share the absence of hydrogen lines with Type 1a supernovae, but physically they are closer to Type 2 supernovae because they come from the core collapse of massive stars. The reason for the missing hydrogen is that these are massive stars that have already lost their outer layers before they explode. A Type 1b supernova comes from a massive star that has blown away or had its outer hydrogen layer stripped off, revealing the helium layer beneath. A Type YC supernova comes from a massive star that has lost most or all of both its hydrogen and helium layers, so the observed explosion is the collapse and disruption of a stripped carbon-oxygen-rich core. Hypernova. This is an unusually energetic core collapse supernova, often associated with broad-lined Type IC supernova. In the collapsor model, a massive, rapidly rotating stripped star collapses, often forming a black hole and an accretion disk. In many collapsor models, the core forms a black hole surrounded by an accretion disk, and jets may be launched by accretion and magnetic processes, though the exact jet launching physics is still an active research problem. This jet then blasts out through the poles of the star at near the speed of light, creating a catastrophic explosion that can be up to 100 times more energetic than a standard supernova. Some broad-lined Type IC hypernovae are associated with long-duration gamma-ray bursts, among the most luminous electromagnetic transients known. Pair-Instability. The theoretical fate of the most massive stars in the universe. This type of supernova is thought to occur in stars with between 130 and 250 times the mass of our Sun. In the core of such a monster star, the temperature is so extreme that high-energy gamma rays can spontaneously turn into pairs of matter and antimatter. This process reduces radiation pressure, causing the core to contract. The contraction triggers runaway oxygen and silicon burning, releasing enough energy to disrupt the star completely. A pair-instability supernova is so violent that it completely obliterates the entire star, leaving no remnant behind, not even a black hole. Superluminous. This is a newer category for any supernova that is exceptionally bright. 10 to 100 times more luminous than a regular supernova. Some may be powered by pair-instability, some by interaction between the supernova ejecta and dense circumstellar gas, and many hydrogen-poor superluminous supernovae are often modeled as being powered by a rapidly spinning, highly magnetized neutron star called a magnetar. The supernova's shock wave slamming into this shell converts a huge amount of kinetic energy into brilliant light, creating an exceptionally bright and long-lasting event. Electron-Capture. This is a rare, in-between type of supernova. It occurs in stars that are on the borderline, not quite massive enough to form an iron core like a regular Type II, but massive enough that their core gets incredibly dense. In these stars, the immense pressure forces electrons to be captured by atomic nuclei. This removes the electron degeneracy pressure that was supporting the core, causing it to suddenly collapse and trigger a supernova. It is a true core collapse supernova, but with a different trigger mechanism filling in a gap in the stellar life cycle. Thanks for watching. Is there something you would like me to cover next? If so, then let me know in the comments down below. Also, please remember to like and subscribe if you enjoyed.